Welcome everyone to my talk. Let me first give a short background of myself. I'm Sriteja Gumita. Currently, I'm working as a research associate at Fraunhofer IEM, Paderborn, and it's in Germany. And I'm also doing my PhD in Secure Software Engineering Research Group that is led by Professor Dr. Eric Borden, who is one of the co-authors, along with Goran Piskasev and Johannes Speth. Today, I'm going to talk about a paper titled Qualitative and Quantitative Analysis of Python call graphs. Let's start with a question. What is a call graph, right? A call graph is a graph-like data structure that connects different function invocation statements, which are also known as call sites, to the functions that are being invoked, which are also known as call targets. And in general, call graph is a very important data structure to perform interprocedural static analysis, whose focus is mainly analyzing how different procedures exchange information. Static analysis for Java in general is the most mature ones, and there are frameworks such as Suite, Vala, which provide frameworks to analyze Java programming language statically. And they also provide static call graph generation algorithms. In the case of Python, it is less, and especially in the field of call graph generation, there are few because Python has a wide range of dynamic features that challenge static call graph generation. So there comes a question to the analysis writer, which static call graph algorithm is best? Answering this question is the main goal of the paper, that is to help analysis writers to select an appropriate static call graph for their needs. Before I talk about the approach, let's first look into why static call graph generation for Python is difficult and challenging. Here I have an example, and there's a class here, calculator, and there is a first function, which is init values. And you can also see that there is an annotation to this function, and such kind of annotation is called a decorator. And here is the implementation of the decorator. In a nutshell, what this function does is it validates if the arguments passed to the function are of integer, float, and complex types. And if the validation is successful, then it goes ahead and invokes the called function. Otherwise, it prints some error string. Note that when a function call to a decorated function is made, the execution in the decorator is executed first, and then the control is shifted to the function that is being called. And here we have a second function, calculate sum, which just prints a sum of two class variables. Here we have a third function, and in this function, we have a template of a Python function in the form of a string. Using this template, a new function can be generated at runtime with the help of inbuilt Python function called exec. And such kind of runtime generation of code is referred to as runtime code generation, and runtime code generation is also possible with another function called eval. There's a final overridden function in this class, getAttr. When an undefined attribute of an object is encountered by Python, the implementation in this function is executed. In this example, we override this method to allow function calls whose name contains sine, cos, and tan in its string. So here we are basically modifying the attributes of the object at runtime, and such kind of implementation is referred to as reflection. Let's look into the main function to understand the example a bit better. And here we have object creation, and then in the second line we have a call to the decorated function init values. Note that the check values, the decorator is executed first here, and then there's a function call to calculate sum, which is straightforward. And there's a final function call to calculate cost. And when we look at the example, such kind of function is never defined. And this can be made possible in Python using reflection. Let's now look into the dynamic call graphs of this example. A dynamic call graph is a call graph that is recorded at runtime. And for this example, we have 9 nodes and 8 edges in total. And let's also look into the static call graphs that is generated by two of the frameworks here, which I will introduce in the following slides. And here we can see that the static call graph edges miss to generate many of the dynamic call graph edges. And these missing edges largely impact quality of any static client analysis. We have taken such kind of dynamic features into account in evaluating the static call graph algorithms that are available for Python. In total, we have evaluated 3 open source static call graph frameworks. The first one is Code2Flow, and it uses regular expressions to generate a static call graph. To be precise, it uses 2 regular expressions, one to identify call sites and the other one to identify call targets. The second framework is Pyan. It uses inbuilt Python AST library to extract static call graph for Python input. AST is an abstract syntax tree, which is basically a tree representation of the source code. The last open source framework that we have evaluated is Vala. Vala in general provides static call graph algorithms for Java, and in the case of Python, it provides one, which is NCFA. Vala uses Jython library to extract the abstract syntax tree of the Python source code, and then it generates Vala intermediate representation for further analysis. To write a meaningful client analysis, the writer needs to understand the limitations of this static call graph. To map this landscape and also achieve our goal to help analysis writers, we have implemented a call graph evaluation framework, which we call eval-cg. And let's now look into the working of this framework. And also let's assume that there is a Python input given to this framework, and I will talk about the inputs in the following slides. So for this Python input, the framework first generates a dynamic call graph. And here we use a tool called PyCallGraph that to generate a dynamic call graph. And this dynamic call graph is considered as a ground truth by this framework for calculation of some metrics. We have implemented framework adapters for the frameworks that I've just described. And these frameworks generate the static call graphs for the respective frameworks. And all the static and dynamic call graphs are present in their own format, right? So to compare them in their source format is a tedious job. So in order to tackle this, we have implemented converters that bring them all to a common format, which is probe format, which is then taken by a call graph analyzer. And call graph analyzer compares static call graph edges with the dynamic call graph edges to generate some metrics. We have developed the framework call graph evaluation framework that can be reused and also extensible in future. We have also made the framework available as a public repository in GitHub. Using eval-cg, we systematically evaluated the static call graphs by performing 2 experiments with different sets of inputs. The first experiment, which we call is a synthetic test. And in this experiment, the input to the framework is a benchmark suite that contains synthetic single Python files. And in total, we have implemented 49 Python programs that are divided into 13 different categories based on the literature and also Python specification. In Python specification, we focused on the items that are relevant to the function calls. In this experiment, PyCallGraph takes each file in the benchmark suite, runs it, and records the dynamic call graph, which is then used as the ground truth. While the synthetic test focuses on analyzing, evaluating the call graphs in terms of their quality, we perform second experiment, which focuses on quantitative evaluation of the call graphs. And we call this experiment real world test. And in this experiment, the input to the evaluation framework is a Python project. And we have selected the Python projects we have selected 5 different Python projects from GitHub based on selection criteria, out of which one is that these projects should have a minimum of 85% of test coverage. And also this project should be well established, which can be seen from total number of forks and total number of stars that these projects have in the GitHub. Before passing this Python project to eval_cg, entry point extractor takes all the source files of the Python project, runs them individually with all the 3 static call graph frameworks, and then filters out the common files that are run successfully from all the static call graph algorithms. These subset of source files serve as entry points to the eval_cg, which in turn serve as entry points to static and dynamic call graph generators. This filtration is necessary as it results in efficient comparison by using same number of entry points in all the call graph generators. In this experiment, we have integrated PyCallGraph into the test suite of each Python project. And so is the reason of having test coverage as one of the selection criteria, which means that when a test case is run, PyCallGraph is also run in parallel, and it captures the function calls and generates the dynamic call graph. And we have only configured PyCallGraph that it only captures the edges from application source code. And for each test case, we have a dynamic call graph. And in the end, all the dynamic call graphs from all the test cases are combined into one, which is considered as a ground truth in this experiment. We performed these 2 experiments to evaluate the call graphs using well-established metrics, such as precision, recall. And along with these, we have also looked into the sources of unsoundness in each call graph algorithm. And we have also judged these call graphs in terms of their running time. Now let's look at the results, starting with precision. This graph shows the results from synthetic test. And on the horizontal axis, we have the precision from 0 to 1. And on the vertical axis, we have the different categories in the benchmark suite. And from it also shows the average, and we used geometric mean to calculate the average. And when we see the results, Code2Flow has the highest precision, followed by Pyan, followed by NCFA. And in some of the categories, Code2Flow and Pyan also provides 100% precision. Now let's look at the results from the real world test. And here is the graph where the vertical axis shows the 5 different Python projects. And even in this experiment, we see the same trend, like Code2Flow is the highest precise, followed by Pyan, followed by NCFA. Now let's look at the results from recall from synthetic test. And here we have a bit of contrasting results. Code2Flow, which was highest precise, is least in recall, which means that most of its edges are not present in the dynamic call graph. And we can see the contrast in the case of NCFA as well, which means a call graph having less precision and high recall says that most of its edges are present in the dynamic call graph. Now let's look at the results from recall, real world test. And here we have a Pyan with the highest recall, followed by code to flow, followed by NCFA. To summarize, while NCFA and Pyan perform better in the case of synthetic tests, in real-world tests, Pyan and code to flow perform best, however, only with 33% and 27% of recall. And NCFA has single-digit metrics for real-world applications in the case of precision and also recall. Now we look into the third research question, which is divided into two, and each research question corresponds to each experiment, synthetic test, and the real-world test. And we will look into the edge statistics in these two research questions. To understand the influence of real-world language constructs on static call graph, we have divided the edges in the dynamic call graph into three types: initialization edges, direct edges, and cardinal edges. We revisit the dynamic call graph from our example in motivation, where we had 9 nodes, 8 nodes, and 9 edges. Yeah. And among these, we have one initialization edge, one direct edge, and there are cardinal edges due to decorators, reflection, and also runtime code generation. Note that the missing cardinal edges have direct influence on support of Python language constructs. We then manually analyze the false negatives of each static call graph for these three types of edges. In other words, we will see how the missing recall percentages are distributed over these three edge types. And these bars shows the total number of false negatives from each static call graph. And from this, we can see that NCFA has least number of false negatives, which also validates that it has the highest recall in synthetic test. Now let's see how these false negatives are split. And this fraction of the edge, this fraction of the bar shows the initialization edges. And there is a small fraction corresponding to direct edges in NCFA and code to flow, and which means that all the three static call graphs are capable of identifying direct edges. The last part corresponds to the cardinal edges, which shows that the support for Python language construct is less from all the three static call graphs. Now we look at the close-up of real-world applications, and this figure shows the edge statistics for the same in terms of Venn diagram. And here the left part of the Venn diagram shows the total dynamic call graph edges, and the right part of the diagram shows the total static call graph edges from each static call graph algorithm. When we look at the figure, Pyan has more number of edges at the intersections than code to flow and NCFA. And then we can also see that the NCFA has almost no edges at the intersections, which means it is not really good to generate a static call graph for real world applications. Let's now look into the final research question, where we judge the static call graphs in terms of their running time. And here we have here the results show the arithmetic mean of the running time from both the experiments, synthetic tests and real world tests. And from this graph, we can say that Pyan generates the call graph in the shortest time. And though code to flow was the second best in case of real world tests, it has huge running time. Yeah, so to conclude, I have first motivated with an example why static call graph generation for Python programming language is challenging, and then also discussed few open source frameworks that are available to generate static call graphs. And then proposed a framework, eval-cg, which is reusable and extensible. And we've performed two experiments using eval-cg. First one to evaluate the call graphs in terms of their quality, and the second one to evaluate the call graphs in terms of their quantity. And the results from these two experiments shows that none of the call graph algorithms are actually good. I mean, in the case of synthetic test, Payan and NCFA provides good results. In the case of real world applications, Payan and Code2Flow provides good results. And we have also seen that NCFA is not suitable for real world applications because of a least number of true positives. And Code2Flow also has a huge running time. So there is much room in the development of static call graph algorithms for Python. With that being said, I conclude my presentation and I'm open for questions. Thank you.
Thank you for the presentation. That was interesting, actually. But let me catch you with this last point. You said there is much room in the development of static algorithms for Python. And what you think would be the next step or the first step in this room for development? What can be changed or improved in these tools?
Regarding these tools, yeah. So from these results, we can also see that which tool lacks which Python feature, basically, and then we can work on improving that part of the feature. And much room in the development of static call graph algorithms also mean that there is there is really not good static call graph generation algorithms for Python. Although these three open source frameworks are available, they are not their results are not really acceptable. So yeah, that's the room of development. I mean, if there is a new call graph that provides good results, then yeah, that would be good. And yeah, we can also evaluate the new call graph to with using eval_cg and see if it performs better than the already available ones.
As far as this, I understand, these call graphs are actively used in static analyzers, right? And static
Yeah.
analyzers, they rely on these call graphs. And now you're saying that call graphs are not suitable for real world applications. So it looks to me like static analyzers may produce wrong information if they rely on that. So you are
Okay. Yeah. What I meant was
so
there are no.
you're shooting the whole world of static analysis right in the foot. Like you're saying you're not applicable to real world applications according to your research, and that's kind of interesting information to many
Uh,
people.
yeah. Yeah. That's not actually what I meant. So there are no good static call graph generators for Python in the case of real world applications. And so there is a much room in the development of static call graph algorithms for Python. And definitely static analysis relies on static call graph. And because there is no good static call graph algorithm for Python, static analysis of Python is challenging.
So before you did this research, you were not sure that static analysis is challenging. So that was your initial, like when you started doing this research, you didn't have the proof that there are problems in this area. And then your research demonstrated I'm just thinking, what was the real purpose of the research? What did you want to confirm or disconfirm?
Yeah, I wanted to confirm if there is a good static call graph algorithm for Python, and apparently there is not.
Okay,
Yeah,
now I
that's
understand.
that's the that's the main goal of the research as well, to help an static analysis writer to select an appropriate call graph. And we evaluated the available call graphs and we found out they are really not good. And among these three, yeah, our research suggests that NCFA is suitable for single files and Pyan is suitable for real world applications. But we they provide really low precision and recall.
And what's your next step? Where do you go from here?
Mm, yeah, next step would be to try and to there is a new paper from ICSI 2021 about a new static call graph, and then so our plan is to first evaluate that along with the eval CG and see if it performs good. If not, then then think about a good way to implement a new static call graph algorithm.
But that's my question. Do you know how to make a better one, a new one?
Not yet.
So during this research, you didn't come up to the ideas of how to improve existing static analyzers. You only analyze them as black boxes.
Yeah.
Okay. Okay. That's interesting. All right, then thank you very much. I think it was really interesting presentation. Well, actually, it's thought-provoking research, that's for sure. We don't know where to go from here. Well, even you don't know. Well, you know you want to create a better one, but even you don't know how to make it. So our listeners will also have to think about this. Let me check the questions. Okay, no questions from there. So thanks for the presentation.